Hello everybody, welcome to Edu-Malanga. We're so glad you're joining us today. On Edu-Malanga we create free tutorial videos that cover the Matric mathematics syllabus of South Africa, and we're starting a new unit today. We're starting trigonometry, and this unit is going to cover compound and double angles in trigonometry. A lot of people struggle with trig, and so what we're going to do is we're going to try and explain everything well. We'll start by doing revision of grade 11 work, and we really hope that this channel is going to help you do very well in this section in your exams, guys. Let's get started then. So what we have on this page is a right-angled triangle. The angle over here is 90 degrees, and the other angle is theta, so it's unknown. And this triangle is sitting on the Cartesian axis, so we have the y-axis and we have the x-axis over here. Let's label it. And what we're going to start off by doing is by deriving the trig identities. These identities are sine, cosine, and tangent. I suspect you know all of this from grade 11, but we're going to derive it anyway just to make doubly sure. So let's get started. This side of the triangle sits on the x-axis, and the length of it we're going to define as x, and this side of the triangle is parallel to the y-axis, and so the length of it is going to be called y. The third and last side is the hypotenuse of this triangle, and we are going to call it h for hypotenuse. So how does the sine, cosine, and tan of this triangle work? There's an expression that is commonly used in trigonometry, and this expression is SOHCAHTOA. From SOHCAHTOA, we can define the sine of a right-angled triangle. Let's use this triangle. We're going to use the angle theta. So we're going to take the sine of the angle theta, and using SOHCAHTOA, it tells us that the sine of an angle is equal to the opposite length over the hypotenuse. So it's going to be opposite over our hypotenuse. That's where the SO comes from SOHCAHTOA. And let's come back to this triangle. What is the opposite length of theta? Opposite length is y and the hypotenuse is h. So we're going to then have sine of theta is equal to y over h. Let's do the cosine now. Again, we're still using theta. The cosine of theta from SOHCAHTOA is the adjacent length over the hypotenuse. So you have adjacent over hypotenuse. That's where the ka comes from in SOHCAHTOA. And let's come back to our triangle. We have adjacent length of x and the hypotenuse stays h. So we have x over h for our cosine. Let's do the last one now. That's our tangent of theta, which is just referred to as tan theta. And from SOHCAHTOA, we can see that it's the opposite over the adjacent length. So it's O over A. And let's come back to the triangle. The opposite is y and the adjacent length is x. And so the tangent of that triangle will be y over x. So that's where SOHCAHTOA comes from. It's an abbreviation that we made up in order to always remember what sine, cosine, and tangents are for a right-angled triangle. So what we've done is to look at these identities when they are in the first quadrant. This is quadrant number 1 of a Cartesian axis. But what happens when you start involving all the other quadrants? When you involve all the other quadrants, that's when you start needing the identity reduction formula. To derive the identity reduction formula, let me first describe this Cartesian axis. Again, this is going to be the y-axis, and this is going to be our x-axis. When we're working with the Cartesian axis, we measure our angles in an anti-clockwise direction, and so we start over here. This is our first quadrant, and when we move in an anti-clockwise direction, this becomes our second quadrant. So this is quadrant number 2. This is the third quadrant. Yes, and this is the last quadrant, which is quadrant number 4. So these are all the quadrants in our Cartesian axis. Let's define the angles of each. In quadrant 1, you have 0 degrees to 90 degrees. So this is the angle, okay? And in quadrant 2, you go from 90 degrees to 180 degrees. In quadrant 3, you go from 180 degrees to 270 degrees. And then the last quadrant goes from 270 degrees back to 0, which is also called the 360 degrees point. And now you've done a full rotation around the Cartesian axis. Remember, this is a Cartesian axis, so our x values are positive on this side when you're going on this way. On this side, our x values are negative though, because you're going to have -1, -2. So here we have minus x on this side. And the same thing happens to y. Y is positive when you are up here. And as you go down, you start -1, -2. And so your y's are negative. We've already derived the trig identities for when we're working in quadrant 1. We used this example over here. Let's start in quadrant 2 and derive the identities. Remember, I just said we measure our angles from the 0 axis and we move in an anti-clockwise direction. So when we were in the first quadrant, we started at 0 and we measured this angle, and the angle was theta. For us to work in quadrant 2 now, we need to start in 0 again, and we need to measure the angle and go all the way over here. So how can we write down this angle? This angle is 180 degrees, and this is theta. So this one can be called 180 degrees minus theta. When you are working with trig identities and you see an angle like this, know that you are in quadrant number 2. Let's write down now the identity reduction formula for this angle. We'll start by using sine again. Let's write quadrant 2 because we're in quadrant 2. And the angle is 180 degrees minus theta. So we have sine of 180 degrees minus theta. Okay, let's come back and look at it. Remember what we said from SOHCAHTOA, sine is opposite over adjacent. So let's look. What is the opposite when we're looking at this angle? Our opposite is going to be y. Y is still positive because we are on this side of the Cartesian axis, and our hypotenuse is going to always be positive. Remember how you calculate the hypotenuse is by saying x squared plus y squared, and then you take the square root. So because you've squared the values, you will always get a positive for the hypotenuse. So in the second quadrant, our sine is going to be, the opposite is y over h, as we can see. And let's compare it to this. Sine was y over h. It's exactly the same. And so you can say which is equal to sine of theta. And this is the first reduction formula. We've just derived it. Let's continue and derive the one for cosine. Cosine, and we're going to keep the angle the same, of 180 degrees minus theta is equal to, let's come back, cosine from SOHCAHTOA is adjacent over the hypotenuse. Our adjacent length is this side. Our adjacent length is minus x. So in this case, we're going to have minus x over the hypotenuse. Let's compare it to the first identity. Cosine was x over h, and over here we have minus x over h. And so what we can say is that cosine of 180 degrees minus theta is equal to minus the cosine of theta. This is the second reduction formula. I hope you're following, guys, because I'm actually deriving them as we work. I want you to understand where the formula come from so that when you have to do it yourself, you don't get confused or get stuck. Let's do the last one for quadrant 2. In quadrant number 2, we're going to keep the same angle again. So we're going to have tan of 180 degrees minus theta. And remember from SOHCAHTOA, the tangent is the opposite over the adjacent. So if we're looking at theta in the second quadrant, the opposite length is going to be y and the adjacent length is going to be x. And so we're going to have y over minus x. Let's compare this to the initial identity that we derived. Our tan of theta was y over x, and this time we have a negative, so that's again going to equal to minus the tangent of theta. And so these are all the reduction formula for the second quadrant. We can see that when we are in the second quadrant, the cosine is negative and the tangent is also negative. So in this quadrant, let's write down, we have that sine is positive. Let's do the same for quadrant 1 as well. When we were in quadrant 1, everything was positive, guys. All our identities were positive. So let's write all are positive. Let's work with quadrant number 3 now. What happens in the third quadrant? First, we're going to have to describe this angle, which is in the third quadrant, from the 0 degree line. So the angle will move like this. Let me draw it in the middle. It'll go all the way to there. This is the 180 degree line, and we've added an angle theta to there. So when we're describing this angle from the 0 degree line, we can refer to it as 180 degrees plus theta. So that's how we refer to an angle that's in the third quadrant. Remember, this one was in the second quadrant. Let's maybe rather write it there, 180 degrees minus theta, and erase it over here. In this quadrant, our angle will simply be theta. So now that we have that, let's derive the reduction formula for the third quadrant. We'll again write down quadrant 3 so that we know what we're looking at for this quadrant. And let's start with sine. Our sine from SOHCAHTOA is the opposite over the adjacent. And what's our opposite length? It's negative y. Y is now negative because we're on the negative y line, guys. This would be negative 1, negative 2, and it would grow from there. So you have negative y, and you also have negative x when you're in quadrant number 3. So what is our sine going to be? Our sine, and we're going to use the angle that we derived of 180 degrees plus theta, is going to be equal to, our opposite length is negative y, and our hypotenuse will always be positive. So our sine of theta is going to be minus y over h. Let's compare it to the original. Our sine of theta was originally y over h, and so this will reduce to minus sine of theta. Let's move on and derive for cosine. Cosine of 180 degrees plus theta is equal to, we come back to our Cartesian axis. Our angle is in the third quadrant, and so we're going to have the adjacent length be negative x. So that will be minus x over the hypotenuse, which always stays positive, is equal to, if we compare to the original, it's going to be minus cos of theta. Minus cos theta. And let's derive the last identity in quadrant number 3, which is going to be tan of 180 degrees plus theta, and that's going to equal to, if we look, we're going to have the opposite length over the adjacent length, so that will be minus y over minus x. The negatives are going to cancel out, and you'll just have y over x, and that's equal to the tangent of theta. From these reduction formulae, we can also see that when we're in quadrant number 3, our sine is negative and our cosine is negative and tan is positive. So let's write it down over here as well. In quadrant number 3, your tan is positive. Let's do the last quadrant now, quadrant number 4. How are we going to define our angle? Remember, this is the 0 or the 360 degree line. And so a very easy way to describe this angle is to say 360 degrees minus theta. For you to start here on the 360-degree line and end up over here, you subtract theta. So if you're defining the angle from the 0-degree line all the way to there, you can simply call it 360 degrees, which is this point, minus theta. It's looking like quite the mess, but I hope you are able to understand and to follow. If you're writing it down, I hope yours is not as messy. But anyways, let's continue and derive the reduction formula when you are in quadrant number 4. We'll again write down quadrant 4. And what was our angle? We'll start with sine. Our angle is 360 degrees minus theta. And what happens to the sine? Let's look. Our sine was the opposite. We still have negative y, but we have positive x on this side, yes, and our hypotenuse will always be positive. So our sine of this angle will be negative y over h. Let's write it down. It's equal to negative y over h, and this simplifies to negative sine of theta. Let's check for the cosine now. We have cos of 360 degrees minus theta, and that's equal to, come back to the Cartesian axis, our cosine of the angle in the 4th quadrant. We're going to have the adjacent length, which is x over the hypotenuse. So that will be x over h, and that will simplify to, from the original, it's also equal to the cosine of theta, cos of theta. Let's derive the last trig identity reduction formula now, and that will be for tangent of 360 degrees minus theta. It's going to equal to, come back to the Cartesian axis. Tangent is the opposite length of the angle, which is negative y, over the adjacent length, which is positive x. So we're going to have minus y over x. And when we simplify this, it'll simplify to minus tan of theta. We can again see that when we're in quadrant number 4, yes, we're in quadrant 4, the sine is negative and the tan is negative. And so what is positive? In here, cos is positive. So these are the identity reduction formula for angles on the Cartesian axis. I hope you understood how we derived them. It's more important that you know how to derive them, the methodology, so that when you have to do it quickly, you can do it yourself. If you are confused at any point in the video, please feel free to leave questions for me in the comments section, and I will try my best to answer all of them. We've reached the end of the video. Please remember to like, to share, and subscribe, and tell your friends about Edu-Malanga. We would like to see everybody do well in their math exams for Matric, guys. Join us in the next video. We're going to do more grade 11 revision.